We can use patterns in maps and cross-sections of hydraulic head contours to infer aspects of the hydrogeology that will be useful. It'll provide some insights about the hydrogeology, and it'll also allow us to interpret the results of groundwater models. So to get started, we'll look at some simple patterns here. On the left, there's a contours, closed contours that are indicating a dome. The highest contours are in the center. And so we can use the green box as a control volume, and we would infer that the highest head was right here in the center. So there'll be a head gradient indicating flow in that direction, that direction, that direction, and that direction. So the head gradient indicates that there's flow out of the control volume in all directions. And that indicates that there must be some flow in from the top or the bottom. And so this kind of closed contour that forms a dome, we infer to be a recharge zone, or perhaps a zone where there's some injection into the aquifer in the form of a well, perhaps. Over to the right is just opposite a basin where the lowest head is at the center, and we have just the opposite inward flow. And so that indicates that there must be some flow perpendicular to the map that would indicate flow out. So that could be a pumping well, or perhaps a zone of high evaporation. But usually these closed contours like this indicate a well. So we can look at a simple example in cross-section, and that's shown here. Here's the water table, right here, this blue line, and here's some control volumes. And so if we just assume that this is homogeneous, then the gradient on the left side of the control volume indicates quite a low flow. The divide is right here, and the gradient on this side is a bit bigger, so we infer larger flow there, and that indicates that there's some flow coming in to make up for the difference. And in all these cases, the gradient is steepening as we go to the right. So the flow in is less than the flow out, and that indicates recharge. So this kind of a curvature of the water table indicates that there's recharge. And if we look at some contours that cross streams, where the stream is flowing in this direction, in this case, what we can do is infer that the flow is in this direction. It's perpendicular to the contours, and it goes from high to low. And that indicates that there's a component of flow in that direction and a component in that direction. So there's a component of the groundwater flow in the direction that the stream is flowing, and there's a component towards the stream. And similarly, on this side, we have flow vectors with components like this. So this kind of V pattern, where the groundwater or hydraulic head contours are crossing the stream and the contours are pointing upstream, that indicates that there's groundwater flow towards the stream, and that means that the stream is gaining. If we look at this example over on the right side, we see that the contours indicate flow like this, and just the opposite from the previous example, there's flow in the downstream direction in the groundwater. The groundwater has a component of flow that is in the direction of flow of the stream, but it also has a component away from the stream. And so this is this pattern is indicative of a losing stream, where the groundwater is flowing, or water is flowing from the stream into the groundwater. So lakes will also have characteristic patterns of groundwater head contours around them. This is a lake where the stage of the lake is 8.3, And we'll just assume that the lake, for our purposes, is at the same head, so that the lake is level. And so this line right here would essentially be the 8.3 head contour. And so if we're contouring every, say, meter, then the 8 contour would wrap around like this, as shown here, and the 9 contour would be wrapping around like that. So flow is perpendicular to the head contours. So we have flow like this, and flow the flow might just be going right around the lake here, but then going into the lake like that. And then the water flows, the groundwater is discharging into the lake on the upstream side, and then it flows out of the lake like this. So this is a flow-through lake. Groundwater is flowing into the lake and discharging into the lake on the up gradient side, and it flows out on the down gradient side. And a lot of lakes are formed by dams. Here's a dam that's impounding this valley. Here's the valley. And this is the lake here, shown in blue. And again, we assume that this is, the lake is all at the same level, and it's at that level. And so we've got a flow pattern that goes into the lake. Groundwater is discharging into the lake on the upstream side. And then on the downstream side, here's the 7 contours. So we have some flow perhaps under the dam, maybe through the dam, or maybe around the dam. So all of those are possible. And again, we have this impoundment forming a flow-through type of water body, with groundwater discharging at one end and leaving the impoundment on the other end. An endorheic basin, or a terminal lake, is a special case. There are these kinds of basins occur as the discharge point for groundwater. So we have flow that goes in towards these basins. So the pattern looks somewhat like a well, except there would be a water body or a zone of high evaporation. These are closed basins, and actually worldwide they're fairly common. This map shows some locations of endorheic basins. In the US, there are quite a few of these types of basins out west in the Great Basin area around Nevada. And you can see worldwide there are a variety of other places. This kind of pattern can be reversed, where the head is highest at the lake and there's flow outwards like this. So the lake is kind of at the center of the dome. And in this case, the lake is acting as a recharge point for the aquifer. And an example of that would be playa lakes. Here's an example from Texas. And these are areas that shallow depressions that fill with water from thunderstorms. And then that water percolates in and infiltrates to recharge the underlying aquifer. Okay, so let's take these patterns and use them when we evaluate groundwater models. Let's take a look at some head contours that are developed from this simple irregular model that we developed last time. So we set up the model and use the baseline parameters that we set up last time, hydraulic conductivity of 10 to the minus 5 and recharge of 5 times 10 to the minus 9. And the stream is represented as a constant head boundary with a head of 60 at one end and a head of 50 at another end. Now this might be appropriate if we knew that the stream was there for certain and had water in it and is a perennial stream then we could put it in like this and run the simulation, and we would get some results as shown here in just a second. This is how the grid is set up. It's a Voronoi polygon grid, and the vertical extent goes from 0 to 70 feet, and that's set up with the grid frame. The rest of it is set up with a coverage called Voronoi. This was described in a previous video, and so here's the grid that I'm going to use. I'll go ahead and run the simulation. And the results are hard to see because it's semi-transparent, so I'm going to make it a little firmer. Also, I'm going to need to adjust the limits on the contouring. The head, that head of 35 is down there in the well, and it's a steep little pocket, and I don't really want to use that in the contouring, so I'm going to make the lower limit a bit above that 35 so that you can see what's going on a little bit better. So that's what the head looked like. And what we see is on the downstream end, the heads are, the contours are pointing upstream, so the stream is gaining, but on the upstream end, the heads are V'ing downstream, so that means the stream is losing. So we can't have a losing stream at the headwaters. That just is impossible. So these are contours that are impossible to occur naturally. And so something is suspicious here. And one of the things could be that the recharge is too low, and this constant head boundary that we've used for the stream is artificially holding up the upstream end of the stream. So we're going to increase the recharge and see what the head look like now. Okay, so now you can see that the head contours form a V that points upstream with this elevated recharge. And I'm going to adjust the contour range here so we can see the heads a little bit better. And you can see that the V's are pointing upstream all the way up to the very headwaters. So that means that the headwaters in this stream are not gaining, but as soon as we get down a little bit, they're starting to gain. And that's pretty close what we would expect. So if we increase the recharge a little bit more, we'll see what happens. This is raising the overall heads and deepening this V. And we've got to adjust the range again. And now you can see that even the headwaters are gaining. Okay, so this is, I think, more reasonable if we have a gaining stream over the whole reach, and we're expecting to have a gaining stream in the headwaters at the very least. So another way that this could happen is if the hydraulic conductivity was actually a bit different than what we would expect. So I reset this back to the baseline, and we can see we have these losing headwaters. And now I'm going to try reducing the hydraulic conductivity by a factor of 5 to 2 times 10 to the minus 6 and run it. And now the recharge is the same, but the hydraulic conductivity has been reduced. And we'll see this is going to cause the hydraulic heads to increase, and it'll cause the V to deepen. And now we've got a stream that's gaining up at the headwaters. So this looks this looks more reasonable than our baseline. So you see we had a reasonable case to start with, and we get a stream that's gaining in the headwaters by either increasing the recharge or decreasing the hydraulic conductivity. Okay, so now we're going to set it back to the baseline, and we're going to look at a different case. We're going to say, well, what if we don't really know if there's water in that stream, We just think there's a stream valley there, and we're not quite sure where the headwaters are. And so in this case, we're going to change the boundary condition that we use to represent the stream from a specified head to a feature that we'll call a drain. It's called a drain in ModFlow lingo. And a drain works like a specified head so long as the hydraulic head in the model is greater than the elevation of the drain. But if the hydraulic head drops below the level of the drain, then the drain is rendered inactive. So we've got to set the drain up. We've got to specify the properties of the drain, the hydraulic heads at either end, just like we did for the constant head boundary that we use to represent the stream. And we'll use this layer range. Make sure to have that checked and set up the condition so that it writes it to the boundary condition to one cell using that layer range property. That'll allow the code to put the boundary condition in the right layer. And now we're going to specify the bottom boundaries of these drains, 60 feet and 50 feet at the two ends. So if the head drops below this value, then the drain will go dry and the model will just ignore it. This was much like you would expect a real drain to work. It looks like I'm trying to find the end of that drain. So I made the hydraulic heads transparent so I can locate it. There it is. And now I can specify the head. And one thing that we need to make sure of is that we specify a fairly high conductance on this drain. I'm using a conductance of 100 feet squared per second. And that's, for this model, that'll be a reasonably high conductance. That'll mean that there's essentially no extra resistance to flow as water flows into this drain. So we run the model, reset the maximum and minimum values for the contours, and we'll take a look at the results. Okay, so this is what we get with this baseline value of recharge. You can see we have contours that are forming a V and pointing upstream right down at the base of the stream, right down there. But throughout the rest of the stream, there's no V. And in fact, as we zoom out, we'll see that the contours are indicating that there's flow from right to left, crossing the stream and going over to that well. So over most of the reach of this stream, the groundwater is simply flowing underneath the stream valley, underneath that drain that we're using to define the stream, and flowing over to that well. It's only right down there at the base of the stream at the discharge point that there's any groundwater that's discharging into the stream. So this is quite nice because it'll allow us to identify the headwaters of the stream without explicitly specifying it. So now we're going to boost the recharge, and this will cause the water levels to rise, and it'll cause the stream to gain over a longer reach. Okay, so it goes right about up to there. That's the headwaters. And up there, the groundwater is below the stream valley. So it flows to the well, and it flows down towards the stream, but it's not discharging to the stream until it gets a bit further down. Okay, so that's elevated recharge somewhat, and now we'll boost the recharge again and take a look again at what this effect is. The stream will gain over a longer reach, and it'll gain even more water. Okay, so that's what it looked like with a higher recharge. And we can see this looks very much like the same kind of a pattern that we would get if the stream was just specified constant head over the whole interval. But by using a drain, we don't have to decide up front where the stream is gaining. So this is a very powerful tool for analyzing the interaction between the groundwater and the stream to which it's discharging. We can also take a look into the subsurface at how the hydraulic heads are distributed around the stream. And we do this by using isosurfaces instead of contours. The contours are lines on the surface of the model, but those lines are actually surfaces of equal hydraulic head. And so we can set up the plot to show these isosurfaces. And that's what they look like. Something that you can see from this is that a lot of these head isosurfaces are largely vertical. This means that the vertical hydraulic head gradient is small. The horizontal hydraulic head gradient is fairly large. That's how the head is changing. An exception is underneath the stream, where you can see the head surfaces wrap around underneath the stream. That's because the vertical head gradient there is larger.